Hello, everyone. Today we are going to talk about quantum algorithms and the power of forgetting. I'm Amin Shiraz Gilani, and this is joint work with Andrew Charles and Matt Coudron. So let's get started. We begin with the scenario we are interested in. Let P be any black box problem that exhibits exponential quantum advantage. That is, there is a query-efficient quantum algorithm for P, but no query-efficient classical algorithm. And there is a small classical proof that certifies the correctness of the solution for P. The question that we are motivated by is as follows. Does there exist a problem P that satisfies these conditions, but there is no efficient quantum query algorithm that outputs some small classical proof of its solution, which we know exists because P satisfies the last condition over here. Let us look at some candidates for such a problem. So can P be the hidden subgroup problem? Even though the above conditions are satisfied, there is an efficient quantum query algorithm that finds a succinct description of the hidden subgroup. So P can be the hidden subgroup problem. Can P be the correlation problem? Correlation does not satisfy the last condition. Namely, there is no small classical proof of its solution. Can P be the welded tree exit-finding problem? Maybe. Let's find out. For those not aware of this problem, we will go through it now. Let us begin by describing the welded tree graph. It is simply a maze with a special entrance and exit vertices, which is formed by joining two balanced binary trees of height n, such that the leaves of these trees here form a 2 to the n plus 1 vertex cycle, and each leaf on the left is joined to two leaves on the right and vice versa. We call any leaf of the binary trees joined to form a welded tree graph a weld vertex. So any of these vertices here is what we denote by a weld vertex. And the cycle joining the weld vertices, the weld cycle. So this big cycle over here will denote it by a weld cycle. We will need to describe colorings and labelings of this graph in order to precisely define our problem. Notice that a welded tree is a bipartite graph with degree at most 3, so it can be edge-colored using 3 colors. We will assume that it is edge-colored using colors red, green, and blue. We label each vertex by a 2n length bit string. The reason to do this is to ensure that it is exponentially unlikely for any algorithm to guess any valid vertex label in this graph. We will be given auricular access to this graph. A welded tree auricle is described by 3 functions specified by colors red, blue, and green, where, for instance, the red function takes as input a vertex V and outputs the neighbor of V with red edge color. We are now ready to define the welded tree exit-finding problem. We are given the auricle we described in the last slide and the label of the entrance vertex, and the goal is to find the label of the exit vertex. Childs et al. Found a query-efficient quantum walk algorithm for this problem, and they also showed that no classical query-efficient algorithm can find the exit. We would also like to mention that this classical hardness result is for the colorless auricle, so it does not directly imply an analogous result for the 3-colored auricle, because a valid three coloring might enforce global correlations in a valid tree graph, which could possibly be used by some algorithm to find the exit efficiently. Recently, this problem was shown to be hard even for polylog depth quantum circuits interleaved with polynomial size classical computations. A consequence of this is an auricular separation between BQP and the class of problems solvable by polylog depth quorum circuits. There is from a concrete connection between the welded tree exit finding problem and our motivational question that we started with. Clearly, an entrance to exit path in the welded tree graph is a classical proof of the correctness of the label of the exit. But so does the degree of the exit vertex, since it is the only vertex apart from the entrance with degree 2 in the welded tree graph. However, the degree argument fails to work for the following variant of the welded tree exit finding problem. A modified welded tree graph is a graph that consists of two copies of a welded tree, with the entrance of the first copy joined with the entrance of the second copy, and the exit of the first copy joined with the exit of the second copy. The corresponding exit finding problem, which we call the modified welded tree exit finding, is as follows. We are given an oracle for the modified welded tree graph and the labels of the two entrance vertices and the two exit vertices, and the goal is to find the correct matching of the entrance vertices with the exit vertices. So one can formally verify that only an even length path from an entrance vertex to an exit vertex is a classical proof of the correct matching. This gives rise to the welded tree pathfinding problem. So let us look at what it is. In the welded tree pathfinding problem, the inputs are the same those for the welded tree exit finding problem. Namely, you are given a welded tree oracle and the label of the entrance vertex. And the goal, as you might imagine, is to find an entrance to exit path. From a classical intuition, these problems seem essentially the same. It might be possible to guess a vertex labeled close to exit, but that is very unlikely. In other words, if you want to find the exit classically, you will need to traverse a path to the exit. Let us consider a naive quorum strategy. Take the quorum walk algorithm of Shiraz et al. And make measurements after each step of this algorithm. But making such measurements will destroy the superpositions, which would constructively interfere later on to get to the exit. So this tweaked algorithm will not be able to find the exit, let alone a path to the exit. Rizmanis considered this pathfinding problem, and he gave what he called a quorum snakewalk algorithm, but he did not prove its query complexity. The community, however, believes that the query complexity of his algorithm is exponential. Aronson mentioned this problem as one of the major open problems in quorum query complexity in his recent article. We now state our main result, which is that there is no efficient, genuine rooted quantum query algorithm for the welded tree pathfinding problem. We have not talked about genuine algorithms and rooted algorithms yet, but we will do that next. Informally, an algorithm for pathfinding is genuine if it only provides meaningful vertex labels to the welded tree oracle. Classically, genuineness is easy to define. We simply disallow any algorithm to feed in any vertex label that it has not seen. It is not so straightforward quantumly though. We do this by exhaustively defining a gate set that we believe satisfies the genuine property. Let's look at some examples of these gates. An obvious one is the query gate, which takes a vertex label and an ancilla vertex register as input and computes the cth neighbor of the input vertex in the ancilla register. Another genuine gate is the partial swap operator. This gate is crucially used in the exit finding algorithm of Shiraz et al. It takes two vertex labels as input and outputs a particular superposition of these labels being in place or them being swapped. The full definition of genuine algorithms includes other gates that generalize these examples. We note that the exit finding algorithm and the path finding algorithm that we stated above are genuine algorithms. Formally state what we mean by a rooted algorithm. We say that an algorithm is rooted if it always maintains at least one path from the entrance to every vertex appearing in its state. That is, for every vertex that it has seen, it knows a path from the entrance to that vertex. This means that finding the exit will be sufficient to find a path to the exit, because we always remember a path to the entrance. We make this assumption because we believe that it is natural to remember a path to the entrance, since the goal is to eventually compute an entrance to exit path. Of course, our result does not rule out the existence of an efficient non-rooted algorithm for pathfinding, and it would be very interesting to figure out if that is actually the case. We now give an overview of our proof. Given any genuine rooted quantum algorithm, we construct a non-adaptive classical algorithm that simulates the given algorithm with a polynomial overhead in the number of queries. Then we show that any non-adaptive classical algorithm for a three-colored welded tree oracle cannot find the exit or a cycle with more than exponentially small probability. It is easy to see that points 1 and 2 imply the required hardness result. We will give a little bit more intuition on our arguments for points 1 and 2, starting with the notion of addresses. An address is basically a sequence of colors. We say that a sequence of colors is an address of a vertex V in the welded tree graph if we start at the entrance and follow the edge colors given by the sequence, then we end up reaching the vertex V. Note that each address is associated with one vertex, that is the vertex that it ends up reaching, but each vertex will have many addresses. We now describe the notion of an address tree. An address tree is like a binary tree. Its root is a vertex labeled empty address, which will be associated with the entrance vertex in the welded tree graph. This component here, which is connected to the root by a directed edge, is here to handle boundary cases such as querying the non-existing neighbor of the entrance in the welded tree graph. For each edge color incident to the address, we draw in this tree an undirected edge incident to the root of that color. Remember that in the example we showed, the entrance had a red edge and a blue edge incident to it. So here we have a red and a blue undirected edge incident to the root. Each non-root and non-leaf vertex have three outgoing edges, one of each color. So for instance, this vertex has an edge of each color incident to it. Each non-root vertex on the left hand side of the tree is labeled by the sequence of colors that you can take from the root to reach that vertex. So for instance, the vertex labeled by R, G indicates that it is the green neighbor of the red neighbor of the root. The address tree oracle is also specified by three functions like the welded tree oracle, one for each color. So for instance, the red function takes an address as an input and outputs its neighbors in this tree with red edge color. Notice that the only degree of freedom in specifying the address tree is in the colors of the undirected edges to the root, which depends on the colors of the edges incident to the entrance in the welded tree graph. This information can be obtained by making two queries to the welded tree oracle. Once these edges are fixed, the rest of the address tree can be constructed without making any queries to the welded tree oracle. Let us describe our classical simulation algorithm. We begin with the initial state that has stored empty address in one of its registers. along with polynomially many ancillary registers that can store addresses of polynomial length. We also allow for some additional workspace. Then we simulate the given genuine rooted algorithm with the welded tree oracle replaced by the address tree oracle. Next, we measure all the address registers of the final state phi of the above simulation, which correspond to these registers over here. Then we query the welded tree oracle for the vertices associated with the addresses that we received in the last step. And finally, we output the resulting vertex labels that we got in step 4. So let us analyze the query complexity of this algorithm. Note that only steps 2 and 4 require querying the given welded tree oracle. We noted in the last slide that the address tree oracle can be constructed with only 2 queries to the welded tree oracle. So we can simulate the second step using only 2 queries. Since the number of addresses and the length of each address that we measured in step 3 is polynomial, the number of queries we make in step 4 is a polynomial times a polynomial, which is still a polynomial. This is the query complexity of our classical simulation is polynomial. You might wonder, why does this algorithm work? Let us use psi to denote the final state of the given genuine rooted algorithm, and recall that phi is the final state of our classical simulation. We show that our algorithm exactly simulates the component of psi, and that does not contain the exit or a cycle. This is because the vertices stored in any basis state in the support of this component of psi will have a one-to-one correspondence with the addresses stored in the corresponding basis state of phi. We also show that the component of phi containing the exit or a cycle is exponentially small, using the classical hardness result for the 3-colored oracle, which we will discuss in a moment. And finally, since psi and phi are valid quantum states, they're normalized. So we have the final state of our classical simulation very close to the final state of the given genuine rooted algorithm. Definitely, this argument is overly simplified and does not cover many cases. For instance, an algorithm could compute a cycle and uncompute it later and pretend to have never computed it. We cannot detect that using this algorithm, but we can extend the ideas we presented here to handle such issues. Let's now discuss some intuition behind our classical hardness result. Consider any classical algorithm that follow a fixed polynomial length color sequence with no even palindromes. That is, it does not backtrack. Analogous to the classical hardness result of Childs et al., we show that it is hard to go back to the entrance or get close to the exit after reaching the well cycle. So once we are here, it is hard to go too far either way. We also show that it is improbable to encounter 2 well vertices that are connected by at least 2 short paths. A key ingredient in our analysis is what we call a color preserving permutation. We say that any well vertex is a C left vertex if it is joined to the left binary tree with an edge of C color. So for instance, these 2 vertices over here are red left vertices. A color preserving permutation is defined to be a permutation of the well vertices such that C left vertices are mapped to C left vertices and C right vertices are mapped to C right vertices for all C, and the well neighbors of a well vertex are permuted according to this permutation. It is easy to check that color preserving permutations maps welded trees to welded trees. An example of a color preserving swap is shown here. If we swap these two vertices in this welded tree, we get the welded tree on the right, which is the same as the welded tree on the left, except for the weld neighbors of these two vertices swapped. So in this case, this vertex is connected to these two vertices over here, but in this welded tree, this vertex is connected to these two vertices. We conclude this talk by reviewing our main result. Based on our findings, if there is an efficient quantum algorithm for welded tree pathfinding, then it must use vertex labels in a critical way, or it must forget the entrance before finding it later along with a path to the exit. There is any such algorithm must be not genuine or not rooted in our terminology. Our work leaves the following problems open. The first and the most natural open problem is to generalize our results about the hardness of pathfinding for efficient, genuine, rooted quantum algorithms to all efficient quantum algorithms, or alternatively, find an efficient quantum query algorithm for pathfinding. An easier open problem is to generalize our results about the hardness of exit finding in the three-colored setting for efficient, non-adaptive classical algorithms to all efficient classical algorithms, or alternatively find an efficient classical query algorithm for exit finding in this setting. These are the references that we use in our talk. Thank you for listening.